Good morning. My name is Derek Gael Bueno Rivera, and I'm going to talk about the elements requiring storage. Okay, the element code segments for translated user programs. A major block of storage in any system must be allocated to store the code segments representing the translated form for user programs. Okay, this holds true regardless of whether programs are interpreted through hardware or software. Now, the system runtime programs. The block of storage must be allocated to system programs that support the execution of the user programs. And the last one is the user-defined data structures. The same block of storage must be allocated for all data structures declared in or created by user programs, including constants. Okay, including those declared or created within user programs. Okay. Now, subprogram return points. It needs a storage allocation, as these subprograms can be called from various points within a program. Consequently, internally generated sequence control information, such as subprogram return points, coroutine resume points, or event notices for scheduled subprograms, must have designated storage. Referencing environments may require substantial space of storage, and temporary expression evaluation requires the use of system-defined temporary storage for the intermediate results of evaluation. Okay? Now, temporaries in parameter transmission. The evaluation of one parameter may require evaluation of recursive function calls. A potentially unlimited amount of storage may be required. Okay? May require it because it may be necessary to store partial results at each level of recursion. The next element is the input-output buffers. It commonly works through buffers, and it acts as temporary storage zones where data is retained between the actual physical transfer of data to or from external storage and the input and output operations initiated by the program. The next one is miscellaneous system data. Okay, storage is required for various system data in almost every language implementation, like diverse system data, including tables, status information related to input and output, and various miscellaneous pieces of state information. Next one, the subprogram call and return operations. These procedures involve the allocation of storage for a subprogram activation record and the local referencing environment, and additional data when a subprogram is called. This allocation progress is frequently a significant operation that needs storage allocation. Okay, the next one is data structure creation and destruction operation. It depends on the programming language features. If the language includes operations allowing the creation of new data structures at any point during program execution, these operations usually demand storage allocation distinct from the assigned during a subprogram entry. Additionally, the language might offer a specific destruction operation, like Pascal's dispose, and many others, of course. And the final element is the component insertion and deletion operations. These operations include for adding and removing components from data structures. Implementing these actions may need storage allocation and deallocation. Perfect. Thank you for your attention.
My name is Daniela Lopez, and today I'm going to present the topic Programmer and System Controlling Storage. First of all, to what extent should the programmer be allowed to directly control the storage management? That's the question. Well, on one hand, C has become very popular because it allows extensive programmer control over storage via malloc and free, which allocate and free storage for programmer-defined data structures. On the other hand, many high-level languages allow the programmer no direct control. Storage management is affected only implicitly through the use of various language features. The difficulty with programmer controlling storage management, it's twofold, and it's presented here. First, it may place a large and often undesirable burden on the programmer, and it may also interfere with the necessary system control in storage management. No high-level language can allow the programmer to shoulder the entire storage management burden. For example, the programmer can hardly be expected to be concerned with storage for temporaries, subprogram return points, or other system data. At best, a programmer might control storage management for local data, and that's it. Yet, even simple allocation and freeing of storage for data structures, and in C, are likely to permit generation of garbage and downlink references. Thus, programmer control storage management, it's dangerous to the programmer because it might lead to subtle errors or loss of access to available storage. Programmer controlled storage management also may interfere with system control storage management in that special storage areas, and storage management routines may be required for programmer controlled storage, allowing less efficient use of storage overall. And well, that's all the bad things that have. But the advantage of allowing programmer control of storage management is that it is often extremely difficult for the system to determine when storage may be most effectively allocated and free. The programmer often knows quite precisely when a particular data structure is needed or when it is not longer needed and may be free. And well, that's the dilemma. This dilemma is by no means trivial, and it's often at the heart of what language to use on the given project. Well, here in this presentation, we are not going to answer that question, but we will help you to take the best decision of choose the best programming language for this topic. Like we can see here, we need to choose the best programming language to program this control storage management. And that's it for my part.
Okay, now we're talking about static storage management. First, it's necessary to define what is static storage allocation, since it is the simplest allocation scheme. It refers to the allocation of memory at compile time or before the program starts executing that remains fixed throughout execution. In static storage management, the size and type of data structures as well as the memory required for them are determined at the time of program compilation, in contrast to dynamic storage management, which we will talk about later. So here, static allocation requires no runtime storage management software. And of course, there is no concept for recovery and reuse. Now, talking about efficiency, static storage allocation is efficient because no time or space is expended for storage management during execution. The compiler can generate the direct L-value addresses for all data items. So the compiler can optimize memory usage and access, what means a better execution time, so static storage runs faster than dynamic storage. And why not? Well, it is incompatible with recursive subprogram calls, with data structures whose size is dependent of compute or input data, and also more memory space is required. among many other desirable language features that are so useful in programming. Nonetheless, there are some languages that are designed for the static storage allocation, like Fortran, where all storage is allocated statically. Also, the second language is COBOL, who plays a crucial role in the financial services sector. This language also uses this kind of storage allocation strategy with the purpose of processing large amounts of data at high speeds. And for the last one, we have C and C++, of course, which have dynamic storage, but also permit static data to be created for efficient execution. And that's all about static storage. Thanks.
Hi, I'm Diana Castro, and first we'll start with the heap storage management, okay? Well, the definition. A heap is a block of storage that allows for the allocation and freeing of the pieces in a relatively instructive manner, right? We can say in simple words that a memory heap is the memory layout where the dynamic allocation takes place, okay? It becomes necessary when a programming language allows allocation and the allocation of memory at any point during the program execution, okay? Some example of this language are include the ML and the LISP. Okay, some pros and cons of the heap. Heap assists you in determining the greatest and lowest numbers. They have like a garbage collection that is a process that runs on the heap memory to free up the memories used by the object. And that's pretty cool. The heap method is also employed in the pretty quick, and it gives you a global access to variables. Okay, this is also kind of a cons, but I'll explain it a little bit more later. Heap has no memory size restrictions. So there will be some pros, sorry. Now the cons of the heap. It can provide the maximum amount of memory that an operating system can provide, okay? It takes longer to compute. And this is the reason why I said that it's also like kind of a con, because it gives you global access to variables, but the con is that it takes longer to compute because the heap memory is used like globally, okay? And the memory management is more complicated. And that's why it takes like too long to execute when compared to the stack. The stack is more faster. Okay, now we're going to see some example of dynamic operation in the two languages that I mentioned before. The first one is in ML. Lists can be concatenated to create a new list at any arbitrary point, and new types can be dynamically defined. And in the LISP, new elements can be added to an existing list structure at any point, okay, requiring a dynamic storage allocation. Some division of techniques of the heap is the storage management techniques can be categorized into two groups. The first one is the fixed size element, and the other one is the variable size. Okay, but later on I'll explain in more detail how they work. Okay, now we're going to see the LISP overview, a little bit of the history of that language. Okay. It's a programming language developed in the late of 1950s by John at the Massachusetts Institute of Technology, okay? LSP stands for list processing and is known for its ability to manipulate the symbolic data structure, and it's used for functional programming concepts, okay? As you can see, it's very old, 1950, but it's still used today. The question is why? Well, the first one is that interactive programming, okay? LSP allows programmers to modify test code interactively, making debugging and developing programs easier, okay? The other one is the symbolic computation, okay? LSP has powerful capabilities for manipulating symbolics, how can I say, data structures. So it's such as lists and trees, okay? The macros. It allows programmers to like define their own syntaxes, sorry, and language construct by using macros, okay? Which can lead to more consistent expressing code. Okay, so that's very cool process. The other one is the AI machine learning. Okay, LISP has historically been used in artificial intelligence and machine learning features, and is still used today in some research areas. So yeah, that's why LISP is still used today. Okay, LISP is commonly implemented by a software enterprise and supports a compiler for selective function definition, but it dynamically nature makes compilation challenging. Why? As I said before, because like we have like global access, and that means that other you're not the only one that are using it, so that makes compilation a little bit more challenging. Okay, the other one is the language utilize garbage collection heap as the primary storage for data programming. Here we have like a visual image that explains what I just said before. Okay, now we're going to the fixed size elements. Okay, so first we need to know like the definition, or what is a fixed size element, what it refers. It refers to the data structure or units of memory that are allocated and recovered in the fixed size chunks. Okay, I like to explain this in other, like in more easy words. I will define the fixed size element as that is related to data element that occupy a constant amount of memory, regardless on the content. Like for example, how can I say? In an area of integers, each element has a fixed size, and the feeder facilities fast and efficient access to the indices. Okay. Some elements of the fixed size is the more memory efficiency. Are often more how can I say, more memory efficient because each element occupies a known of a content amount of memory. Like you already know how much memory you have, so it can be a little bit more tightly controlled, and this can be beneficial in some scenarios. Okay, the other one is the random access, right? Accessing element in the area with a fixed size element is typically faster than the variable size element. Indexing into an area is the constant time operation. Okay. Now, the predictability is the size of the data structure is known at the compile time, leading to more predictable and deterministic behavior. Like you already know the size of the data, okay, and that's like makes things more easier to know how to manage the memory. The other one is the simple implementation. Implementing data structure with a fixed size element can be simple, and especially for algorithms that rely on the constant time operation. Okay, some uses case can be the area with a known size. You already know the size, so it's have no problem with the memory. Okay, it can be like a little bit more tightly. Where's the concept here? It can be tightly controlled. Okay, and this also in a situation where memory efficiently and predictable access time are crucial, right? The other one is the variable size elements. Okay, what is like the difference between, okay, or what is a variable size elements? Variable size elements refer to the data elements whose memory uses can change based on their content. Okay, for instance, in a text string, the amount of memory it takes up on a vary because the length of the string may change. Okay, so it's more flexible than having a fixed size in this case, right? So, but it can make memory management a bit more complex. Some variable size elements are the dynamic usage. Variable size elements are more flexible and can adapt to varying data requirements. This is useful when the size of the elements is not known. Okay, so you have like more options, and it's not so tightly like the other one. So yeah, the other one is the space efficiency. In some cases, variable size elements can be more space efficient, especially if the actual data size is smaller than the allocated space. Okay, it reduces wastage. Okay, with a variable size element, you can allocate exactly the amount of the space needed for each element, reducing potential and memory wastage. Okay, so yeah, I think this is one of the best pros, okay, of the variable size element. And in the fixed size element, we don't have this. Okay, now the complex data structure. Variable size elements are often used in more complex data structure like linked lists, trees, or dynamic arrays where the size of each element may vary. Okay, it can change. So yeah, in some use case can be the list, the linked list, and the other dynamic data structure, as I said before, and the situation where the size of the data is not known in advance or it can change, right? So that will be all for me, right? And thank you.
Hi everyone, I'm Olaf, and I'm going to talk about the suggestions. This basically is an overall of what we have just seen. Here we have the most text on compilers, construction trees, stack, and static storage allocation strategies. Let's remember what is stack and static storage. Stack in Spanish pila is the one that goes the variables, or yeah, the variable, not the variables, the elements goes one on top of another like this. However, in a stack, you just can get the element on the top, and the storage, the static storage, is a yeah. There's also another called dynamic storage that it can span or compress as long as the program goes by. However, in the static storage, you declare since the beginning how much space is gonna need. So for this kind of problem, like the stack that you just can get one element at a time, we use the heap storage management, and it's that has been widely studied. And yes, of course, basically in the heap you have all the elements you want or you need, and you can get them. Yeah, you can get any of them. However, the only problem is that they are not organized. They are or mixed up. Like there is not a specific order. Is what I'm trying to say. That's why we have some techniques such as the LISP and the ML. This is for heap storage. Both kind of try of making things a little bit easier to find, making lists, but they are still free, the elements inside the heap. We also have the operating systems also provide storage management facilities that often overlap the facilities provided by programming languages. This means that the operating system we're using right now, it also already has some storage techniques or some storage facilities, as it says. And we're using another facility when programming. It overlaps, like it helps you. It gives you a boost or a bonus, however you want to see this information. Also, we have virtual memory. Systems are commonly provided by many operating systems to provide storage allocation in fixed size pages or variable sizes segments. These facilities may support, but usually don't supplant heap storage management. We are talking about the static management, the static and the stack that is there. Well, actually, stack and heap, they work together. They complement one another. Also, I would like to add is that the garbage collection recovery as a method of recovering information sometimes is not worth it because the cost of storage management. Let's put it this way: if you want to recover a tiny amount of information and you use this method, it will cost you a lot. I mean, a lot of storage. However, if you want to get back a massive amount of the information, this method will really help you, like to don't waste or to optimize the storage you have. That's it for me. Thank you very much.